Hello, hey, my name is Lee. I'm from the data infrastructure side of Lyft, and right now I'm leading a few initiatives within the data infra. One of them is Spark on Kubernetes, and Rohit will talk about some of this.
Hello everyone, I'm Rohit. I work with Lee on the data platform team at Lyft, and previously I worked at the data platform team at EA and VMware, and Spark on Kubernetes is one of the projects that I'm also focused on. Okay. So today's agenda, we have a few things lined up. So first we want to introduce you to the data stack at Lyft. What are the challenges that we face today with the current architecture? How does Spark on Kubernetes help us? And as we are trying to productionize this system, what are the challenges that we are seeing? So data landscape at Lyft, this slide basically gives you a very high-level view of technologies that we use. I'm not going to dive very deep into this, but on the streaming side, we use like Kafka, Kinesis, Flink, Beam. For our compute systems, we use Hive, Tez, Hadoop MapReduce. We use Presto for ad hoc querying. We use Druid for more real-time analysis. And we have some BI tools like Superset, Mode, Tableau, which gets used. And we are also on a couple of cloud platforms. This slide basically gives you a history of how the compute team has evolved over at Lyft. And over the last 3 years, the company has grown a lot. So back in 2016, we started with a vendor-based Hadoop solution. And at that point, mostly it was just MapReduce jobs. Then within a year, there was a lot of adoption, a lot of data growth, and then it was mostly Hive and MR. And we started using Presto at that point. In mid-2018, which is last year, most of our workloads were then running on Tez. And we started using Spark mostly for a lot of machine learning use cases and some ad hoc use cases. And then late 2018 and up to now, we have been investing in our in-house Spark on Kubernetes infrastructure. And we have gone working closely with our customers, like going through different phases, a lot of customer acceptance tests and things like that. So what is batch compute used for at Lyft? So if you look at this slide, on the left-hand side, we have like the disparate data sources, like event data, all of our operational data stores like MongoDB and Dynamo and all of those. So this CDC and event data then flows through Kafka Kinesis, and then it splits off. So the data either all of it gets written to S3, or then we ingest a subset into Druid for more real-time analysis. And once the raw data is in S3, we do the actual batch compute where it's mostly Hive and Spark. And then after that, we use S3 as our data warehouse, so data gets written back to S3. And then that's where our different users, which is like different use cases, including ML and engineers and data scientists, they start interacting with the data. So from the previous slide, diving a bit deeper into the batch compute piece, what you would see is that we use Airflow as our orchestrator, and then we have a third-party control plane which helps us like provision clusters. Basically, we did a lot of work in-house to scale this, make this highly available and more reliable. And then once the data gets processed on these clusters, they get written to S3. We have like some custom data lineage tools built in-house. There's a project called Emonson, which got recently open sourced from Lyft. And once all of this data is processed, like we mentioned, like people use like Superset or Mode or Tableau to actually process this data. So what are the challenges that we see today with the current architecture? So first is that we use a third-party vendor solution. So there's definitely some dependencies that comes based on that. Data ETL is today solely expressed as SQL. So we'll be diving a bit deeper into each of this, but that's basically kind of like restricting the usage of how complex the logic could be. We have different dependencies in terms of like Hive, Spark, if you're using some like packages, like all of this adds complexity in maintaining these clusters. And then because of these dependencies, we have to kind of run homogeneous clusters. And we really want to run heterogeneous just to improve the utilization overall. So what comes with third party? So one other thing is it's proprietary code. We exactly don't know what's the code running. There could be possible patches. So it gets really complex debugging issues at times. You could use something like a bootstrap technique to plug in your own custom bootstrap stuff, but that could be inconsistent and it is error prone. You have to stick to the release schedule of the vendor. So even if you want to use a feature from possibly a newer and an older version, it's quite tricky. And you are really stuck with a homogeneous environment because, again, you have a lot of dependencies per job. So moving on is SQL, the complete solution. So this slide is basically an example of a complex SQL trying to do a lot of regex parsing and all of that. So we see a lot of pattern like this internally. And in fact, we have seen queries which are as long as a couple of megabytes. So people are really trying to do complex stuff in SQL. What about Python? So Lyft is a very Python-friendly shop, and people love to use Python. We use it a lot for our microservices. And Lyft also has a lot of geo-based data sets. So people really want to use these geo libraries that are available out there with Python. So how does Spark help? So Spark helps, if you look at this slide, there are 4 dimensions. So one is definitely it helps us like easily interact with different data sources and sinks. It supports a few different schedulers. So that's a win for us, like it supports Yarn and Kubernetes. Spark has plugins for basically interacting with Python, Java, Scala. So that's basically wider adoption. And then there are numerous different ways you could interact with Spark. So after adopting Spark, what does the challenges that still remain with us? So one is, again, per job dependency. So if you start using PySpark, you have this case that you would be depending on some Python version or some Python package. And then what happens is basically if you have a single cluster doing this, you have to really handle your bootstrapping very well. And then you end up in a model where you would possibly running many clusters for many different stacks, and that is an operational overhead. So this is just an example of some of our popular packages that we see. People love to work with Pandas, NumPy, Apache Arrow. Also, people love to use different features. They would reach out to us that, oh, there's this particular version in Spark X version that we want to use. And then that again means that we would possibly have to either support them through a separate environment or then look at complexity of supporting in a single environment, which would mean making sure there's backward compatibility. So how does Kubernetes help? For Kubernetes, I think the biggest thing is being container native, and that's the biggest win. It helps us handle a lot of these dependencies very well. The other thing is multi-tenant, so that works well in terms of our idea to run heterogeneous workloads on a single cluster. It has good support for operators, which makes it really extensible, and also it is very like declarative and immutable. So that's a good feature. So this slide is really tough to look at, but what we are trying to say is that there's so much momentum going on in the open source community in terms of Kubernetes, and Lyft in general is also moving towards Kubernetes. All our microservices stack is on Kubernetes. So there's over a lot of momentum, and it's really easy to reach out to open source and get support on issues that we run into. So even after adopting Kubernetes and Spark, there are some challenges that remain. So Lee would be diving deeper into this in future slides. For our current scale, we are in terms of tens of petabytes of data. We have about 100K batch jobs running daily. We are on the order of thousands of EC2 nodes, and we have about thousands of workflows which run daily. So now I would give it over to Lee to dive you into the more interesting parts.
All right. Can you hear me? Thank you, Rohit. So how do we scale? So scale is a big word. So there are many dimensions when we start scaling we are looking at. In this particular slide, there were many dimensions we examined. Some of them we actively invest in, as those highlighted here in pink. So this is our current evolving architecture, and it's very similar as our initial batch architecture, but pay attention closely to there's the 3 additional Kubernetes native components. One is a workflow orchestration component. One is the infrastructure gateway, we call controller cluster. And then we have similar way in the middle. We have similar set of multiple clusters, we call compute cluster, or is a Kubernetes cluster, and they are all connected through a service mesh. So one of the interesting things we examined is this multi-cluster approach. We divide our multi-cluster approach based on abstraction, the concept we call labels. In the gateway, we can dispatch separate different Spark job based on label to a pool of clusters. In this example, you can see there's labels, there's a many-to-many mapping between labels and clusters, and that mapping is dynamically managed by the gateway. And within the clusters, within the pools, we have different clusters. The clusters are serving as a pool of work that can share, doing load balancing between those workloads across many clusters, and each cluster itself, since we're running on AWS, they are also managed by the ASG. Also, the clusters, there are distinction between those cluster pools. Some of them can share the same persistence for different types of workloads. Some of them has their dedicated persistence for security compliance reasons. But for us to have a universal data discovery lineage, we do all the job clusters share the same set of metadata for discovery schema and a lineage. This is one of the examples why we bring this concept of cluster pool from the control cluster. So in the one reason we use is clusters, we can do cluster rotation, and while providing HA high availability within the pool to serve certain workloads for different cluster labels. Another reason for this HA support is once in a while we need to upgrade our control components within this cluster, and during that moment of maintenance, the cluster is not available for serving workloads. Another construct we introduced in our solution is we call namespace groups. So we noticed at a very early stage when we start experimenting scaling Spark on Kubernetes, we noticed there is some practical limit on number of active pods you can launch in a single Kubernetes namespaces. As you all know, if you run Spark on Kubernetes before, you have to specify a namespace at the Spark submit time. But by that time, you already tied your Spark job to a specific Kubernetes namespace. But sometimes the namespace can be very crowded. So what we did here is we introduced a namespace group, which can group certain namespaces as a single group, and we can dynamically dispatch the jobs to within this group to a different namespaces depending on the crowd list of these different namespaces. Another reason we use namespace group is we have this concept of multi-tenant roles. So one group can match to one type of IAM role on the AWS, another namespace can map to another IAM role. So you can have a separate access control and a separate also the sidecar configuration when you only ingest different logging requirement and metrics requirement. Another concept that we introduced when we're looking at the different dimensions of scale is pod sharing. So one of the issues we encounter when we scale Spark and Kubernetes is the high pod churn rate when you are running batch jobs. Because some of the Spark jobs is very short living and constantly spinning up and down a Kubernetes pod, will create a stress on the both Kubernetes API server and Kubernetes etcd quorum. So what we did is we find out some of our jobs, when we do deeper dive of some of our jobs, we noticed there are certain jobs, they can share the same dependencies. So we basically encode this as an envelope of the containers, and we can call into a share path, and those jobs will use a share context using, right now we're using the fair scheduler within a single Spark context to run those jobs. Those jobs mostly are the SQL-based jobs. Another aspect we look at when we start looking into this pod sharing, we discover some of the different volume of commands that launching on our Spark clusters is majority of our workloads, I would say, almost like 3/4 of our workloads are DDL commands from our production Spark jobs. So in those cases, for most of the DDL commands, what we did to further reduce the pod churn is separation. So we separate our DDL commands through this job controller. I will talk about more about what's inside the job controller. But at a high level, the concept is we split them at the routing level. For the DML commands, most of them will ship to Spark API server and go through a Spark operator to launch a Spark pod. But for like the 75% of our job, those DDL commands, they will use the pod sharing through a Spark Swift server, and this Swift server is also sitting behind operator and controller we developed to do auto scale. There are other dimensions. We also looked at it when the cluster is become oversubscribed. One of them is pod priority and preemption. It's still a work in progress, but the idea is we bring the pod priority and the preemption concept that's introduced in Kubernetes 1.10 into this picture. But unfortunately, when we experiment, we noticed there are certain issues that have not been addressed in Kubernetes since 1.10, and only recently in Kubernetes 1.14 they addressed some, which released a couple of weeks ago, and which addressed the issue. So right now, this one is still our experimental feature, and it's working for certain workloads, but not all of them. One more thing we looked into is separation, resource isolation between nodes and jobs, and also the load labels and the load selectors. So why we doing that? Because resource isolation is very important on the Kubernetes, because Kubernetes is a multi-tenant system. So we not only have those batch ETL jobs running, we also have, for example, on the bottom, I have an example. There are certain workloads in deep learning workloads, they need GPU loads exclusively to perform. So we introduce those taints and labels to isolate these loads physically through those. And then when the scheduler comes in, we introduce the tolerations and load selectors to make sure certain components only run a subgroup of those loads. Also, this one is important for our control plane. The control plane, we'll talk about more about the controllers. The controllers and the watchers, those ones will run on dedicated, we call core loads, and those ones will not execute or schedule the Spark jobs to isolate the different network traffic. One other dimension we looked at and we also noticed in our environment is since we are running mostly on AWS, our ECR is our Docker registry, but unfortunately, when we launch so many Spark jobs with so many different Docker images, the ECR sometimes fails. So what we come up with is using a daemon set, which is a concept in Kubernetes, which you can bootstrap on individual loads. You can think about daemon set as a bootstrap for individual Kubernetes load. So we launch that and pull certain base images into those loads when the ASG spin up new nodes into the Kubernetes cluster. And when the job starts running, most likely the images are already there, or only very small incremental layers need to be pulled from the Docker registry. Okay, this is another interesting part we introduced. This is one of the components inside our job controller we call the config composer. What the config composer does is enable us to dynamically adjust the Spark job configuration before we actually submit through the Spark operator. Like I mentioned earlier, when you submit the Spark job, you already know which namespace, how big the job, and how many executors and so on you need. But in certain cases, that information may not fit into your target namespace. So what this config composer does is it watches the different changes and the different events from the Kubernetes API and notice certain changes and overlay those changes on top of these different defaults and the user-specific config until we reach a final configuration, suitable configuration, and by that time, then send to the Spark operator to launch your actual job. Okay, this is the internal components of our job controller. The job controller roughly can divide into two sets of components. So the job controller, obviously we have an endpoint for our end user to interact or our client tools to interact. We have a REST API endpoint. It's very lightweight, but majority of work is goes through the bottom part, which is the watchers and controllers. Some of them are implemented as CRD, the custom resource definition within Kubernetes, and they share some control plane storage, which is a mix of S3 and the relational database. To mesh this whole thing together with our control cluster, they talk to our control clusters through the Kafka message bus. On the right side, to launch the actual individual systems components, we do have the Jupyter Notebook service for our data scientist workbench, and for some of the long-running pods like the shared Spark pods, this is also managed by our controllers as well. These are some examples of our what are the controllers or watchers we have. Obviously, we have a job router and a scheduler within our controller, which decide which cluster to which namespace to run and which names group to run, and what is and what are the binding of the different security contexts and so on. The namespace controller is mainly decide which namespace is available within the namespace group to host this Spark job. Config composer we talked about. The service controller, which manages this different long-running Spark services, mostly the Swift services and the notebook services, the Jupyter or Zeppelin services, mostly Jupyter. On the events watcher side, we do have metrics and event watchers, which watch the Kubernetes layer, which can give us feedback constantly about the current state of this different namespace and the different load labels, what capacity are there, and so on. And the Spark job here, both Spark job and Spark CRD, which the Spark operator creates, all those events and metrics we also watch and analyze and also send over to their two routes, send over to our metric store, and also inform our config composer. This is Spark operator. We use this one heavily as our Spark job launch on Kubernetes, and I want to give a special thanks to Yilan from GCP, from Google Cloud. He developed this one in the beginning, and we collaborated with him closely to help us make a higher level abstraction on the Spark job on Kubernetes through the CRD concept. When we developed this solution, we used a lot of different monitoring and logging toolbox for us to understand what's happening on the cluster and also across different clusters when we can do a holistic picture. So on the cluster, we use Prometheus for most of our metrics and for analysis individual cluster level metrics. And also Statsd for our data collection across GMX and as well. And we do use Heka and Fluentd mostly for logs ingestion from the individual nodes and for our individual pods. Heka is a sidecar which you can inject into your Kubernetes pod and also into your into any of our long-running service pod like Jupyter and so on, which can ingest a log into Kibana. We also, at a multi-cluster level, we do use a third-party vendor, which is SignalFX, to aggregate some of the Prometheus metrics across across multiple clusters to give us a holistic view when we're looking at a cluster pool level metrics. This is a very interesting example. At the beginning, when we start launching, when we start this journey, in the beginning, when we launched Spark jobs on our single namespaces, we noticed the OOM queue in the Kubernetes world is very different from what we see on YARN. So that's a lesson we learned while we are developing this solution. Another part, when we're talking about this different multi-cluster solution, how do we do this provision and automation? So when we're talking about so many different Kubernetes clusters, it's non-trivial to automate all these different components and make it work as seamless as possible. So we invest heavily in our provisioning and automation tools, mostly the combination of this Jinja template, KS deploy, customize the 3 components to automate our Kubernetes, Kubernetes layer components. We also use, we invest heavily on those different sidecars, injectors, and secret injectors, and so on. Demos that we already talked about. And on the AWS side, obviously, it's Terraform and Jenkins pipeline and so on to automate the AWS layer automation and provisioning. I talked about a lot about the different kind of solutions. There's still a lot more remaining work we're actively working on. One of them is improve our the efficiency and resilience of our job routing and scheduling capability and the job config composer settings. Right now, it's only working for namespace level and namespace group level, and we want to make it even more dynamic, so the jobs can ship can rolling among different clusters within a cluster pool. So we have more resource optimizations there. Our end goal for this whole project is we want to bring as closely as possible serverless, a self-serviceable user experience for an end user to do any data source to any data source data compute. I know in the earlier diagram we showed we mostly for S3, but we start seeing use cases of our customers. They are ingesting from any to any, which is an interesting use case. Cost distribution, it is effort within this project. We are ongoing with Kubernetes since there's we are doing a lot more monitoring tool and metrics collection within those events. So we are building more cost distribution pipeline on top of that. Docker image distribution, that's another one we are still looking into, although I mentioned earlier we are looking at this demo set to pre-populate some of the Docker images. But even with that, there is limitations of how much we can do with that solution. We are still constantly improving and re-evaluating our solution. Obviously, there's an earlier talk about Spark 3, what's coming. And in combination with Kubernetes 1.14, we are looking forward to this bright future where when we combine these two, we should have a even more scalable solution in the future. This is just a recap. And Spark can unify our batch compute use cases, and using the Kubernetes, it can solve many of our dependency and multi-version issues that our customer encountered in the past in our vendor-based solution, and also can help us evolve faster across these different types of use cases, including the GPU-specific use cases on a multi-tenant environment. And using this multi-cluster-based solution and service and compute mesh-based approach, we can scale Spark on Kubernetes significantly comparing to what a single cluster can achieve. But still, we are still seeing we still see challenges to scale that even further. So we are still working on, and we would like to engage the community to drive this solution forward. So we are constantly engaging with these different communities, the Spark maintainers, the Kubernetes community, the Cloud Native Foundation, and obviously Spark operator with the Google Cloud and so on. And with that, I conclude our presentation. Questions?
We have about 10 minutes, so yeah, there's a lot of time for questions. Question, you mentioned a couple of times about GPUs.
Yes.
Yeah, here. So like you separated out using node labels and all that stuff, right?
Right.
So how are you, I'm guessing you are using some kind of distributed training. How are you using it from Spark? What frameworks you are using? And another question is, like you mentioned, mostly you're using S3, right? So
Right.
are you accelerating, like for example, storage from storage perspective, so that GPUs don't get starved? Do you have any idea about that?
That's an excellent question. So let me repeat your question. So how do you make sure the GPU loads are not starving? Actually, right now, we don't do that cost optimization yet.
Okay.
We group this different class, we call the load labels, but through the implementation is basically through the different ASG on AWS. And sometimes we do see there could be a lower utilization, but that's where our next step is. We want to gather the metrics of the cost utilization, the utilization of this cluster, and do optimization there. Yeah.
Yeah, and the other question was, like, are you using distributed TensorFlow or Harvard kind of thing? How are you driving GPU workload from Spark? I'm sure you're using some distributed training.
Excellent question. So question is, how do we use, what do we use for the distributed GPU workload? So unfortunately, I'm not the best person to answer that question,
Okay.
but I know we do have the TensorFlow that's written together with Spark, and
Okay.
that requires GPU for this workloads. We typically we enforce the Taints toleration, so those jobs can run on GPU. But what exactly those jobs run, I do not know.
Okay,
Yeah.
sure, no problem. Thank you.
Yeah, sure.
Outstanding talk. I have a question. You have the slides you had, so mentioning the out of memory things, and you said was the different behavior between Kubernetes and the Yarn. Can you explain what's really going on here?
Yeah. So what we noticed on Kubernetes at the very beginning of our exercise, when we investigate, is unlike Yarn typically has a certain toleration of your memory overusage before Yarn resource manager kill your container. But on Kubernetes, the kill is very abrupt. So which means if you overuse even with a fraction of a second, your pod can be killed. So it's a different experience from the job perspective.
So it's mainly the maturity of.
It's very aggressive pod killing comparing to what Yarn used to have.
Okay, great. And so at this point, what's the stage of your the Kubernetes usage on Spark? It's kind of the experimental, or it's like your production use?
We already running a pre-production workloads for some of the use cases. We have quite a handful of clusters in this multi-cluster solution. It's we are not fully production yet, but we are close.
So they are currently you are using Yarn, or what's
You mean right now
in the production?
Yeah, right now the existing Spark jobs are running on Yarn. Yeah.
Thank you.
Yeah.
Hey guys, thanks for the talk. So you've got this really built-out jobs architecture, and then a couple of times it was also mentioned that you've got Airflow in there for a layer of workflows. So you've got jobs and workflows, right? Now, is each step in the workflow kicking off a job, or is that still firing off like a raw container? Just what is that? How do the two kind of live together?
You want to answer that?
So basically, in terms of Airflow, you can think of like one particular task. For example, you're running Spark SQL. So there's going to be one task that's going to spawn off the Spark SQL query to our API layer. And then once it comes, we use like our container images to actually run the SQL. So it's probably like a mapping between a task and an actual job on the Kubernetes side.
Okay, so it just kind of is lightweight, tracks the completion, and then.
Yes.
Yeah, okay.
Yep.
Thank you.
Yep.
Hi, I was curious about resource isolation and whether you're using Kubernetes resource quotas. We've bumped into some trouble trying to integrate those with Kubernetes on Spark operator.
Sorry, can you repeat that question? What kind of issue are you seeing?
Well, are you leveraging Kubernetes built-in resource quotas, and have you had any issues with their interaction with the Spark operator?
We use resource quota on the namespace level. We don't use on the individual Spark job level.
Cool. Thanks.
Yeah.
So all of this, like, extra complexity and operational burden just to solve for dependency management and that sort of thing, like, was it worth it?
Excellent question. So, yeah, so sometimes you have to make extraordinary complexity here to make the end solution as simple as possible for end users. Our goal is to provide a serverless, self-serviceable Spark as a service to our end user, regardless of what dependency you have and what kind of jobs you have and where you don't care where you run. In order to enable that vision, we need to go this extra complexity to make that a reality.
Hi. My question would be, have you done any other comparison with other container management solution? Is there something available out there? Kubernetes versus ECS versus Mesos versus few other container management solutions?
Excellent question. So at the beginning of this project, we examined a few. Mainly is Mesos. Obviously, Mesos is the one earlier container orchestration. But when we look at this momentum, the community momentum behind Mesos and Kubernetes, we see there's a clear advantage going Kubernetes, although it's still in the early stage. But with the strong community behind, we think in time, this Spark on Kubernetes will make the first choice for running Spark on containers.
Also, Amazon recently announced the native support for Kubernetes that they are providing the managed service, EKS. By any chance, have you guys explored it?
Excellent question. So the question is, have we evaluated EKS from Amazon? Yes, we did. But as a company, Lyft, we have the strategy to go within the company. We want to own our Kubernetes infrastructure, so we decided to go with our company-wide Kubernetes provisioning service.
Thank you.
Yeah. Cool. Thank you.
Thank you.